Okay, so now we're up to the next problem. And so this problem, well, it looks like it's got a little more to it than the last one because it's not a ratio of polynomials. I mean, the numerator's not a polynomial, the denominator is. But so no worries, we'll pretend that we can just, use substitution to evaluate that. So if that's what you try to do, which is what you should do initially to see what happens. But if you do that, you can see you end up with a fifth minus a fifth over 0, and you end up with 0 over 0, and lo, it is an indeterminate form. So what that means is we need to do some algebra. Okay, so we're still looking at this second problem, and the message that we have when we need to do algebra, and the algebra is not something simple like factoring, the message is here. Perform the operation. And that message is going to go for this problem and for this problem as well. So what's the operation here? Well, in the numerator you can see there's a subtraction problem. And it involves the subtraction of fractions. So what we're going to do to perform the operation is we're going to subtract those fractions. So to subtract these fractions we need a common denominator. The common denominator in this case, since these are relatively prime, in other words they have no common factors, since they're relatively prime, the common denominator is the product of the denominators. And so our job then is to multiply each of the fractions by some version of 1 so that they can each achieve the common denominator. So for the first fraction you can multiply by 5 over 5, and the second fraction you can multiply by 5 plus h over 5 plus h. These are both versions of 1, and when we do that we can see that the two fractions will now have the common denominator. Now the numerator in the first case is just 5, and in the second case the numerator is 5 plus h. But you have to remember that between these two fractions there is a subtraction sign. So what we need to do then, since the denominators are the same, we can subtract the two fractions. Here's the common denominator, and we have the first numerator, subtract the second numerator. But the second numerator is a polynomial, so this negative sign gets distributed to both terms in the sum here. So this would be minus 5 minus h. That's a very common error that students make. They would just subtract the first term and then subsequent terms they wouldn't apply the negative to, and that would be an error. So here's the new numerator. 5 minus 5 is 0, so we're just left with negative h in the numerator, and then here's the denominator. So the original function is algebraically equivalent to this one. So this limit, the original limit, which was an indeterminate form, is algebraically equivalent to this limit. And so now, and this is a ratio of polynomials, so we'll try again to use substitution, and substitution works because in the numerator we get 0 and in the denominator we get 25. 0 over 25 is defined, and that's equal to 0. So then I thought, well, like before, I'd like to show you the graph to verify that it makes sense vis-a-vis what the function actually is. So I took a picture of that here. Here's the function, and this function for hold on one second. I need to look on my computer. Okay, so you can see that I have this function graphed, and the window I used, x min is negative 3.7, x max is 3.7, and on the y, for y min that's negative 1.1, and y max is 1. So this is a window. It's a special window. It's a version of the zoom decimal, and the zoom decimal is a good window to use because the 0 pixel, I turned the axis off so you could see it. This gap right here, that's when x is equal to 0. I use trace, so if you use trace you'll see this is when x is equal to 0, and you can see there's a hole there because there is no y value, and that makes sense because this function is not defined when h is equal to 0, or equivalently, if you use the calculator to graph this, it's not defined when x is equal to 0. But if you do a trace, you can see this, it approaches 0 asymptotically as x gets large. That also makes sense because as x gets big, the denominator gets big, the numerator stays pretty small, so as x gets big, this will asymptotically approach 0. So that's what's happening at this end, but here is the here's that missing point where the function's not defined at 0, and so we could, I didn't do it here, but you could write a piecewise defined function that's equivalent to this one. That piecewise defined function would be equal to this expression when h is not equal to 0, and it's undefined when h is equal to 0. So that's what it would look like. But here we can see that the graph is consistent with our result, which is 0.